In this last video, we're going to go over the model calibration problem. The model calibration problem is basically the inverse of the uncertainty propagation problem, and that's why we often call it the inverse problem. It goes like that: you observe a quantity that is predicted by your model, and you want to characterize how this observation changes your state of knowledge about the model parameters. So you're basically observing something that your model predicts, and you want to go back and say what were the parameters that gave rise to this prediction. In the trailer example that we saw in the previous video, let's say that we don't know, for example, let's say we have a pretty good idea about k, m, and maybe the velocity with which we're traveling, and we don't know y naught and l, the amplitude of the road roughness and the wavelength of the road roughness. But let's add a sensor to the trailer that measures the amplitude of the oscillation, and that sensor gives us the measurement xm. And I have noticed that I have separated xm from x, which is the actual amplitude, because the sensor gives us a noisy version of the true amplitude. It doesn't see exactly the true amplitude, it sees the true amplitude plus some noise. So that's why the measurement node is distinct from x, which is the actual value of the amplitude. But the measurement is nevertheless the child of the measurement node, so of the amplitude node. It is the true amplitude that is affecting what you measure. It just happens that you don't measure exactly that, you measure that with some noise. Now, the only thing that I want you to observe here before I introduce the calibration problem for this particular case is that I have made the measurement node gray. So I'm using this color to indicate that this node has been observed. So if you see a node in my causal graphs that is filled with some color, this means that this node is observed. So here xm is observed, none of the other nodes is exactly observed. So all the other nodes are more or less random or uncertain. Okay, but xm is actually observed. It has a specific value that you have seen. Now, the model calibration problem in this example consists of updating your state of knowledge about, let's say, y naught and l if you see xm. That's pretty much what you want to do. So if you have, let's say, a pretty good idea about k, m, and v, because our uncertainty about them was very tight, okay, then xm will mostly be affected by y naught and l, and basically by observing the amplitude, the maximum amplitude of the oscillation of the suspension, you can infer y naught and l, or update your state of knowledge about them, because it may actually be impossible to tell what they are exactly. Alright, so the formal solution to the model calibration problem goes as follows. You first quantify your prior state of knowledge about all the model parameters, and this is what we actually did as part of the uncertainty propagation problem in the previous video. And then you use something called the Bayes rule to condition your prior knowledge on the observations in order to get your posterior state of knowledge about the parameters. So there's a formal way, a formal mathematical way of taking what you knew and conditioning that on what you observed. And that conditioning tells you what you should believe after you make the measurement. Now, the whole point of this class is to create a practical procedure that characterizes our posterior state of knowledge. So, in other words, the mathematical problem, the formulation of the calibration problem is more or less trivial. Okay? It is very straightforward to formulate the mathematical description of the calibration problem, and we're going to learn about this as part of this class. But it is tremendously difficult to carry out the program suggested by this mathematical formulation. And we're going to spend quite a few lectures talking about how it is that you can actually carry it out.